algorithmically synthesize a circuit or a milli machine which satisfies the requirement for all possible inputs. So here the circuit, takes a sequence of inputs, up to the current clock cycle, and it produces the current output. This power set of O and power set of I may confuse you a little bit, but remember, we have a set of wires I, and at every clock cycle, a subset of them will be high. So it will be a member of the power set of I, similar to the power set of O. So the current state of the system is basically given by the set of wires which are high and the set of output wires which are high, right? And this is basically the Church synthesis problem. He posed the problem, and it was solved by Bucke and Landweber in '69 using what are now called Bucke-Landweber games. Okay. A further development of this problem came with quite a seminal work of Ramajan Vanham in two initial papers in Siam Journal of Control and Optimization in '87 and '89. And what Ramajan Vanham asked was the following. They talked about synthesis of controllers from regular assumed guarantee specifications. So suppose we have two properties, DA and DC, which are regular. What do we mean by these properties being regular? Well, basically they are equivalent to a finite state automata. So these properties basically correspond to something called a monitor automaton, which will monitor the behavior of the input wires and the output wires at each clock cycle. And basically they will say whether the behavior so far, seen so far, meets the property or not. That is, you can think of this as a DFA, which is observing the system inputs I as well as the system outputs O, and at every clock cycle, it will either be in an accepting state or a rejecting state. It will be giving out a green light or a red light. And as the system evolves, it will be giving out green light or red light at every point. And this automaton is finite state. So in Vanham Ramaj's work, DA and DC were actually such finite state monitor automata, right? DA was the assumption automaton, capturing the valid behaviors of the plant and the environment. The environment should be well behaved as well as the underlying plant which you are trying to control should be well behaved, and all those constraints would be incorporated into the assumption automaton DA. And DC was the commitment automaton, which was saying what was the desired behavior from the controlled plant. So we had two automata, DA and DC, and the aim was to somehow come up with a milli machine which will ensure the following. Invariantly, at any clock cycle, if the assumption automaton continuously was showing green light, that is, assumption held at all points in the past of the current point, then the commitment automaton should also be showing green light. So if the assumption held continuously in past, the commitment should hold at the current point. This was the requirement.
Paritosh, question.
Yeah.
This DA, it is looking only at the input wires, or DA also looks at both input and output?
So DA can actually look at both input and output wires, but there is of course a causality issue here, right? Between DA and DC. So if you make very strong assumptions, if you make assumptions like DC should be met, then clearly the commitment DC will be met, right? So DA can look at input and output wires both.
Okay, thanks.
There is no requirement that DC should be there. And so, sometimes, for certain DAs and DCs, the problem may be unsolvable because of this circularity. What you want is a causal construct, function which will generate suitable outputs which will satisfy DC, right? So what we want to output is a circuit or a milli machine which will satisfy this property.
Paritosh, Rahul here.
Yeah.
Is there a simple example just for me to understand what DA and DC will look like?
Yeah, so I can give you an example. suppose, I think we will have this example a little bit forward. Let me jump to it a little bit. Maybe it will help getting it here. So suppose we have a synchronous bus arbiter, So this is the kind of arbiter that sits on your PCI bus or something like this. Suppose there are 10 cards connected to the bus, and at every cycle, of course, a subset of them will request to become bus master. The job of synchronous bus arbiters is to arbitrate between this request and give out acknowledgements. So you've got requests R1 to Rn. Some subset of them will be true at every clock cycle. And you've got acknowledgement lines A1 to AN. And exactly, at most one of them must be made high to allow the corresponding card to become the bus master. Okay?
Yes.
This is the broad idea. Now, commitments would be something like, mutual exclusion of acknowledgements. That in any cycle, simultaneously, it is not the case that both AI and EJ are true. Right? And this should be invariantly true for every cycle. But the assumption, also there may be response time requirements, which may say something like this. If it is the case that the ith request has been continuously true for k cycles, right? Then I should get acknowledgement during that period of k cycles. So in any window, if the request has been held continuously high for k cycles, then the acknowledgement should be true. Now, suppose you have got 10 request lines and you want to respond to all of them within 3 cycles. This is impossible because all of them may request all the time, and all of them may not. You may not be able to respond within 3 cycles. That's clear, right, Rahul?
Yeah.
So you will make an assumption that at a time simultaneously no more than 3 requests come.
So is it fair to say that the DA is some set of lots of if conditions?
Yes.
And DC is a set of feasibility constraints that applies to the system?
No, DC is your requirement.
Okay.
Is something that the synthesis algorithm has to check.
Okay.
You may give, absurd requirements which are not solvable. In this case, the problem becomes, the circuit is unsynthesizable.
Correct.
But you should detect that if that is the case.
All right.
Yeah. Okay. So this is the church synthesis problem, and it was solved by Bucchi and Landweber in '69. Okay, but this is a very pessimistic view of, this is a very weak kind of requirement on the controller. It says that if the assumptions are continuously made, then you will meet the commitment. If the assumption goes wrong even once, from then onwards, there is no requirement on the controller to behave in any sensible way, right? So this kind of synthesis is called the B-correct synthesis. And unfortunately, now there is a synthesis competition tied with the leading COW conference on formal methods. And all of the synthesis tools which compete basically work from this B synthesis goal. So this B synthesis goal has been looked at length. But robustness deals with the ability of the synthesized controller to meet the commitment even under some intermittent violations of the assumption, right? So if you observe the behavior and if the assumption has red lighted a few times, you should still be able to, try and meet the commitment as much as possible, right? And such a controller would be called a robust controller. Yeah, this is the idea. Now, how much of violation of assumption should be tolerated? There are various notions in literature. For example, there is K-robustness notion due to Bloem and co-authors, which says that at any point in the behavior of the circuit, the count of number of violations of the commitment is upper bounded by some constant K times the number of violations of the assumptions, modulo in the initial part by some constant M, right? So the ratio of number of commitment violations to the number of assumption violation is upper bounded, right? And that is called K robustness. Another notion was what was called KB resilience due to Eller and Topku, which says that circuits may recover if the assumption violations stop for a sufficient amount of time. So a recovery period of B cycles, would allow my system, my controller to recover from errors. So if it is the case that after at most K assumption errors, there must be a recovery period of B cycles. And if this condition holds throughout the execution of the system, I should continuously satisfy the commitment. This was called the KB resilience. And it's quite popular. Then there are other quantitative synthesis techniques where you assign rewards and punishments to assumption violations and commitment violations, and then you play some quantitative objectives you have, like mean payoff or ratio gains, and you can try to synthesize controllers to meet these quantitative objectives. Now, of course, these are all good approaches. But some issues with them are that the notion of robustness is defined semantically. Each notion is different and it is on the behavior of the system. Given this DA and DC automaton, the robustness is actually, on the behavior, semantically defined. And so for each notion of robustness, a separate synthesis algorithm is given. And there is no simple way of comparing these different notions of robustness. And each different notion of robustness requires discovery of a new synthesis algorithm. What we try to do in this work is we try to give a kind of logical specification of robustness. That is, we specify robustness by giving this assumption formula. In our case, instead of automaton, we give a formula of logic called QDDC, which will play the same role as the automaton. A commitment formula and an additional formula called the robustness criterion, which will capture the our intention of what kind of assumption violations should be tolerated.
So I have a question.
Yeah.
So in the previous slide, when you were talking about robustness for this mean payoff,
yes,
is it with respect to some sort of perturbation on the weights? And
no. Every commitment violation will incur a certain penalty, and every violation of the assumption will give you some amount of reward. And then, or maybe these are two different measures, and you take a ratio of these two measures, if you like.
Okay.
Right.
So in the case of mean payoff, what is the assumption, and here what is the guarantee that we are looking for? So the guarantee, I understand it should be...
Assumption and guarantee are given by this automata. And every time the assumption automaton red lights, you incur a certain penalty on that transition.
Okay.
Every time you red light a commitment automaton, you get a reward of a certain value.
Okay.
What you want to do is you want to keep the total reward within certain bound, or there are the mean value of this payoff that you get from this is bounded, upper bounded, lower bounded, stays above 0. So there are if you read these papers, they will make this precise.
Okay.
Right.
Yes. Yeah,
so
thank you.
Violation of assumptions and commitments are discrete Boolean events that occur at various points in the execution, but they invoke certain quantitative amount of rewards and punishment. Okay. But what I'm talking about is, a slightly different track. So let me move on. Okay. So we have this specification format for specifying the robustness in the controller behavior logically. And what we will show is this will allow us to encode many of the existing notions and to define a large number of new notions of robustness. Now, given such a logical specification of robustness, we have a uniform synthesis method. That is, given any triple DA, DC, RB, we will try to synthesize a controller. And this will invoke both what are called hard and soft robustness criteria. So we'll see what these are. Okay. And because we have this logical formulation for the same assumption and commitment, we can play with what are the different notions of robustness by this robustness criteria. We are able to compare different robustness criteria, and we can synthesize controllers against this different robustness criteria, and we can actually compare their performance. So we are able to actually, do some sort of experimental comparison of the behavior under different robustness criteria. Okay, so that is what we try to do. Now I have a long journey and I'll try to be more conceptual than technical in the talk. It's late in the program. So I'll give you a brief introduction on our logic QDDC, in which we specify both the assumptions, the commitment, and the robustness criterion. 3 formulae in the robustness specification, logic QDDC. Then I'll give you the exact logical specification of robust controller and what it means. Then I'll give you a repertoire of different robustness criteria, at least some samplers of what can be stated. Then maybe if there's time, we will go into synthesis method. Then I'll show this very briefly, and I'll show you some experimental results. Okay, so we have a long journey. Now, temporal logic formula, as I said, specify evolution of system state in time. That is the state of input wires and output times at every clock cycle, how they evolve in time. Constraints on those are written in the logic. This has, of course, fairly distinguished past. Amir Prueli in 77 came up with linear temporal logic and showed it was relevant to describing communication protocols or digital circuits or protocols in computer architecture, things like that. And he went on to develop fairly comprehensive theory of how to check the programs, given a design and desired property, how to check whether the program has the desired temporal logic property or not. That is, all behaviors of the programs for all possible inputs, do they meet the property or not? And he initially worked in a proof theoretic way, that is, he gave some axioms and proof rules by which you could establish these properties, but also worked on what is called model checking. Emerson and Clark gave a different logic called CTL. I won't go into the detail, but the later trend was to do algorithmic verification. That is, given a design and a property, to try to develop an algorithm which will check whether the system has the desired property or not. And much of the work sort of concentrated on finite state systems with very large number of states. And the idea was to actually explore the state transition graph, which is large but finite, and to check whether the properties hold or not. So all of this, both of these work went on to lead the, get their Turing Awards. Now, LTL and CTL are the dominant market brands of temporal logics. There is an extension of this called PSL Sugar, which is an IEEE standard used by most of the hardware industry, But foolishly, we decide to use a different and a homegrown variety of logic to specify things. Well, it's not as foolish. The logic is called QDDC, or Quantified Discrete Duration Calculus. My friend Kamal Lodhia prefers to call it Quidditch, right? And it's actually the discrete time version of a logic called duration calculus, proposed by Zhao, Hoare, and Ravan for, way back in 91. So maybe it's not so stupid either, because Hoare was involved. And, for those of you who already know temporal logic, I'll just recount some features. It's discrete time because time is counted in terms of clock cycles. It's an interval temporal logic. We'll see what this is. And it includes measurements of counts of number of events that occur within certain kinds of intervals. Okay, so we'll see this. And it includes temporal quantification. That is quantification over variables which evolve with time. Right, so it's quite a powerful logic, but why go for such a logic when there are already LTL and CTL? And I need to defend this a little bit. So let me give you some sort of ontological foundations of this logic. Our view is that activities that occur in programs, take time. They span time intervals. And the activities are composed of sub-activities. Sub-activities span sub-intervals. There are interesting relationships between these intervals of sub-activities. They may overlap, both may start and end at the same time, saying that they are exactly concurrent, or one may start exactly when the second one may finish. So it is this kind of things that we want to express in our logic. It's a bit like difference between Fortran programs and structured programs, where you've got sub-programs and you compose them using an if-then else, or using sequential composition or parallel composition, rather than talking about what is the next assignment to be executed and the next assignment to be executed, right? So here is my example. This is my way of making an omelette. Making an omelette takes time. It spans a time interval, starting at this starting point and ending at this point. And making an omelette involves sub activities. So the first sub activity is breaking the egg, which spans some sub interval. As soon as breaking the egg finishes, I do the following sub activities. This is my recipe. I start singing a song, and the song starts at this point and ends at this point. And while I sing, I do two further sub activities. I beat the egg followed by fry the egg. So your chop here is the followed by operator, and making the omelette, interval implies there is a sub interval of breaking the egg followed by the activity within this sub activities within this bracket, which involves singing the song concurrently with beating the egg followed by frying the egg. So this is the kind of description you want to give, and you can generalize this to behavior of robots, which must first move to the end of the road and then take a turn and then move the arm. So there are phases of behaviors, and they will have such description. So this is the kind of description you want to give. Second reason is that you want to make quantitative measurements, and these measurements are naturally associated with time intervals, not time points. Okay, so for example, you want to say it rained 3 inches in Mumbai in last 24 hours. You have this time interval whose quantitative measure is 24 hours, and during that you make a measurement of amount of rainfall and you put a constraint on it. It rained 3 inches during last 24 hours. This is the kind of thing. Or the probability of photon decay in 1 second is so and so. TFR physicists tried hard to come up with this value. Didn't work out. Okay. But here is a property from our bus arbiter. In any interval of 15 cycles, so that is in any observation window of 15 cycles, if request is continuously high for all of these 15 cycles, there must be at least 3 acknowledgements somewhere within this 15 cycle window. So any 15 cycle window where request is continuously high must have 3 acknowledgements. And this can be written in our logic QDDC by a formula like this. And I'll try to give you enough vocabulary to understand this formula. So what we get experiences are very visual and a highly expressive language. It's hard to reason about, but it is highly expressive and highly succinct. So this is the flavor. In temporal logic, what happens is you don't talk about observation intervals and what happens during them. You sit at a time point and you talk about what happens in future or past. So you've got this one point and you're describing how things look from that. Whereas in interval logic, you have these 2 points and you're describing what happens within the observation window between those 2 points and some other windows related to it. Okay. It's an interval temporal logic. So what is a behavior? A behavior is evolution of observable wires in time. Time is clock cycle. So on top, I am writing positions or clock cycles. Clock cycle 0 to 9. And suppose we have only one wire P, we plot its value at every clock cycle. At 0th cycle, it is 0. At 4th cycle, it is 1. At 5th, it's 1, etc. Now, given such a behavior and a time interval B, such as 4 to 7, the shape of the logic is that we can calculate whether the property evaluates to true or false for that observation window B. That is, a given property is true for interval 4 to 7 within this given behavior. So you're given a behavior and an observation window, and you ask whether the property is true of that observation window or not. Now one kind of formula is very simple. Double square bracket P, where P is a proposition. A proposition can be evaluated at a clock cycle, at a time point. But what we say by double square bracket P is that P is invariantly true in the observation interval. So this property, invariantly P, will be true for the observation interval 4 to 7, because between 4 to 7, P has, value 1 throughout. It will not be true for the interval 2 to 7, because somewhere within that interval, P becomes false. So square bracket P says invariantly P. SLN gives the step length of the interval, that is E minus B, where interval is BE. And S count P counts how many times proposition P was true during that interval. So if you take interval 2 to 7, S count of P will be, 1, 2, 3, 4, 5, right? And what you can do is, you can compare such a measurement, the length of the interval or the count of some proposition, with a constant. So you can only compare measurements count of certain conditions within an interval or the length of the interval with integer constants. That is what you are allowed to do. Okay, and modality box says for all observable intervals, for sub-formula D should hold. So we have vocabulary like this. So if I go here, it says something like this. For box says for all observable intervals within the behavior, if it is the case that within my observable interval, if antecedent of this implication is true, the consequent must be true. The antecedent says if my interval is such that the request is continuously high throughout the interval and the length of the interval spans 14 steps, that is 15 cycles, then the number of times the acknowledgement occurs within that interval should be at least 3. So within any 15 cycle window, there should, where request is continuously high, there must be 3 acknowledgements. This is the kind of properties we are able to state, right? And it's kind of hard to state this economically in logics like LTL or CTL. Okay. So here is the logic. I don't propose to go in it. In red is its syntax and in blue is its semantics, but let's not go into technicalities. So far we are talking about a formula holding in an interval. What we want is a formula holding at a position within the behavior. So we say that a formula D holds at a position I in a behavior sigma if formula holds for this interval spanning the entire past of I. That is for the interval 0 to I. Right? So if the entire past of position I, the interval spanning the entire past of position I satisfies a formula, we say that the formula is past satisfied by point I. Now, if given a finite behavior sigma, we say that the formula D holds for that behavior if it holds at the end point. That is, for the entire interval spanning the starting point of the behavior and the ending point of the behavior, if the formula holds, then we say that the behavior satisfies the formula. And hence, with a formula, we can associate all the behaviors which finite behaviors which satisfied. There is a language view of the, there is the language view of a formula. A formula is a set of finite behaviors, okay, and there is a language. Now, typically we recognize languages by an automaton. Here is another way of defining languages, and this brings us the question of interconnection between languages and automata. And I talked about initially automata, which will observe the behavior and be, give green light or red light, right? Equivalently, we can have a formula which will accept the behavior so far or not. And so, formula will also give green light or red light as a behavior evolves, right? So I hope this logic automaton view connection is clear. Now, of course, what kind of languages can we define using formula for logic? Here is the theorem. We can only state regular properties and exactly the regular properties in our logic. So for every formula of our logic QDDC, we can effectively construct a finite state automaton with the same language. So there is the language of the automaton and there is a language accepted by the automaton. There is the language of the formula, and the two are the same. Conversely, if you give me any finite state automaton, I can effectively construct a formula such that the two have the same language. And yet, the descriptive power, the descriptive vocabulary of these two mechanisms, the logic and the automata, are quite different. So a useful thing is this connection between logic, a formula and its formula automaton, the so-called monitor automaton for the formula. Such formula automaton are useful for many purposes. You can use it.
Paritosh. Hi, Paritosh. This is Arkadev here.
Sorry, Arkadev. Yes, please.
Yeah. No, just a silly question. So you're saying, given logic, you can convert it into an automata and vice versa.
A formula in our logic.
Yeah. But then, when you say that, however, the expressive power of these two things are different, what exactly do you mean?
Yeah. So I said no. In that, the way in which they describe properties is very different. For example, we can talk not of a property or and of a property, even other operate. There exists a certain propositional variable such that the property which includes that variable holds, right?
Yes.
So we have this kind of operations, which are, ultimately can be done by automata, but at great cost. So one of the problems is the succinctness. I didn't want to go into this. I have many slides on properties of this logic, but to cut a long story short, let me go into complexity.
So do you mean like the,
for example, succinctness? For a formula of size D, we can show that the lower bound on the size of the smallest automaton, which is equivalent to it, will be non-elementary in its size.
I see.
Right? So you can describe things extremely economically for some formulae.
I see.
Right?
Mm-hmm. Okay.
Also, in terms of vocabulary, the kind of things that you can say in logic, some things are good, some things are not good, this is good and this is also good. So I want to jointly both to hold. These kind of things are kind of, you have to do it using closure properties of automata.
Sorry, one last question, Paritosh. So when you when you implement this kind of things,
yes,
eventually, there's a compiler that will probably, compile.
The last line, this tool called DC valid.
No, but my question is, do such compilers ultimately convert this into an automaton?
Yes.
But then there is, okay, so then the I see. So therefore, the advantage only is only within quotes is that of the convenience
at the requirement specification level.
I see.
The other thing is, this automata that you convert, you use quite sophisticated techniques to construct this automaton efficiently. Although the worst case complexity is non-elementary for most specifications of interest, with some smart automaton construction algorithm, you are able to construct fairly huge automata and to represent them in computer memory fairly efficiently. So use BDD-based representation for the transition tables. See, take naively a formula over, let's say, 50 Boolean variables. The alphabet of the corresponding automaton is 2 raised to 50, right? Because every variable may be true or false.
Right.
You're not going to be explicitly able to write this automaton down naively, right?
Okay.
So you'll use special symbolic representations of these automata to write these automata and explore them. I didn't want to go into the automata side of this. I know this is interesting.
Okay.
Yeah, but I would love to talk about this later. See, I'll show you flash one slide since the question has been raised. So here is an automaton, right? With 3 states and one reject state where all missing transitions go. And you can represent it using what is called semi-symbolic automaton by, whose transition table is given by some sort of decision, tree, which is optimized as a DAG. What is called reduced ordered binary decision diagram with multiple terminals. So we used empty BDDs to represent automata, and that allows us to work with fairly huge automata. But ultimately, it's an automaton. So you are right. In a reductionist way, all we are doing is we are doing logics in place of automata. But that in formal verification is a very respected line of inquiry and also practical use, the logic automaton connection. So why are such automata interesting? I have these 3 lines. Given a logical formula, you can check the validity or satisfiability of the formula by constructing its automaton. You construct the finite state automata corresponding to it and minimize it. If you get a single state automaton with only accepting state, the original formula is valid, right?
Yes.
If it has at least one accepting path, it is satisfiable. You want to check whether one formula logically implies another. What you check is language of the first formula is contained within the language of the second. So you do language inclusion problem on automata, right?
Right.
You can also use this automata to visualize some good behaviors and bad behaviors, which are models or counter models of your formula. So automata are very useful, and you do want them, right? They can be used for what is called runtime monitoring, property-based testing, and model checking, right?
Right.
So we do build this formula to automaton constructor. You are right, and what you call compiler. And in fact, for this logic, we built the compiler way back in I think in 87 at TIFR. It happens to be one of the very few model checkers to come out of India. I will not go into its details, but in a series of papers, we checked, applicabilities and efficiencies of this automata construction, the data structures for it, and to what kind of problems they can be applied. But there is a tool which will basically apply this theorem, the first bullet of this theorem, and also analyze it for things like what is given in the second block, right? Validity, satisfiability, etc. So we have this tool called DC valid. This is old work, right? Here is the example of the arbiter that I gave to Rahul. You have n request lines. At every cycle, a subset of them is true. And the job of the arbiter is to set at most one of the acknowledgements true, to one of the requesting cells. And the other requirement is this response time, that in any observation window, if a particular request is held continuously high for k cycles, then there should be at least one acknowledgement. So, the latency, or the response time of this arbiter is k cycles. That is, any request which is continuously held for k cycles should, get a response. And here I have a sample behavior for a 2 request arbiter. So on the first track is the pattern of requests coming in the clock cycles given by pause number. So at clock cycle 0, there are no requests. At clock cycle 4, both of them are requesting, things like that. And the acknowledgements given out, are at the 4th cycle, the acknowledgement A1 is given, A2 is not given, so this is how, the circuit evolves. And you can say that, our response time is 2. That is, if you hold the request true for 2 cycles, you must get an acknowledgement. So, for example, if you take the window 4 to 5, R1 is continuously true as well as R2 is true. And we can say that between this window 4 to 5, this interval 4 to 5, both the requests are true simultaneously for both the cycles. And of course, both of them get a response within that window. So the response time of 2 is met, right? If you go to the window, 6 to 7, this is not true, because, acknowledgement is given only to the first request for both the cycles. The second one was also requesting for 2 cycles and it did not get any. So some intervals satisfy this, some intervals don't satisfy it. And if you look at path satisfaction of this formula, at 0.7, there exists an interval in its path, the interval 6, 7, which violates this property. So at 0.7, this requirement will red light. Up to 0.6, it will green light, right? So we can write requirements like this, and the church synthesis problem is to automatically design a controller which will meet these requirements. So that is the job. In this example, there are no assumptions, right? Here is the actual automaton or the milli machine automaton, which is a monitor automaton, which is produced by our tool DC synth for DC valid for this requirement formula. And what you can see is from any state, if you simultaneously produce 2 acknowledgements, you will go to the reject state and stay there forever because you have violated the requirement. Also, if the requirement is true simultaneously for 2 transition, then the corresponding acknowledgement must remain true. So I will not check this out, but such monitor automata can be constructed. Now, in this monitor automaton, there is one thing I would like to say. So this monitor automaton is for the 2-cell arbiter. For each transition has a label 4-bit vector. First 2 bit vectors give the value of the request, and the next 2 bits, the last 2 bits of the column vector, give you the values of the acknowledgement. Now, you can see that from state 2, on request R1 and R2 both being true, you have 2 possible transitions. You can give acknowledgement A2 and go to state 4, or from 2 on 1-1 input, you can give output A1 instead of A2 and move to state 5. So this automaton is actually output non-deterministic. Although it's a deterministic automaton, from the same state on the same input, there is possibly 0 or more outputs possible. There may even be 0 outputs possible, and you may go to a state, with red lights. So that is the shape of this monitor automaton, right? And what is the synthesis problem? Let's come to the synthesis problem. The robust controller requirement is given by 3 formula, an assumption formula, QDDC formula called DA, which is equivalent to the assumption automaton, a commitment formula DC corresponding to the commitment automaton, and in the be correct notion, which is what most tools do, what you want to synthesize is a controller which will choose among possible outputs those outputs which ensure the following. If the DA automaton continuously has been green lighting, then you choose those outputs which will make sure that the DC automaton also green lights. If the DA automaton has been continuously green lighting in past, then in the current transition, DC automaton should also green light. This is so invariantly you satisfy the property if all the prefixes of the behavior seen so far satisfy my assumption formula, then my behavior, current behavior should satisfy the current formula. In robustness, we want to satisfy DC even if DA has been false for few of the prefixes, right? And so what we do is we try to specify a relaxed assumption. And how the assumption is to be relaxed is given by a formula called RB of A. So RB of A is a kind of generic specification of how any given assumption DA is to be relaxed. So RB of A is given independently of DA and gives the generic requirement of how the assumption should be relaxed. And then we compose this user given formula, assumption formula DA, which is specifications, which is problem specific. We compose it with this robustness criterion RB of A, and we derive what is called the relaxed assumption. And it usually specifies something weaker than prefix of DA, right? So RB of D, here is an example. RB of DA may state that DA evaluates to false at most 3 times in past. And what you want to do is you want to synthesize a controller under this hard robustness requirement. That is, you want to say, and if the relaxed assumption RB of DA is true, then I want to satisfy the commitments. And this is, I'm sorry, I keep jumping. Yeah. So you have this hard robustness requirement which says that if relaxed assumption RB of DA is true, not necessarily the strong assumption prefix of DA or continuously in past DA, but this relaxed assumption RB of DA is true, then I want to satisfy DC. And for example, if you take this red colored example RB of DA, it says that if DA has been evaluating to false at most 3 times in past, I want to continue to maintain the commitment. So I will tolerate up to 3 assumption violations, right? And of course, we will talk about various different RB of A's which are specified by logic, and for each one of them we will have a hard robustness requirement. So hard robustness requirement says that I will guarantee that the commitment will hold provided my relaxed assumption holds. And if the relaxed assumption does not hold, then there is no requirement from the hard robustness side for the commitment to hold. If the relaxed assumption does not hold, I have choice of many different outputs and my controller may behave arbitrarily. Maybe it will behave even adversarially and make DC false in every such case, right? So my hard robustness only guarantees that the commitment holds provided my relaxed assumption, not as tight as pref of DA, relaxed assumption holds. This is called hard robustness. But we can also talk about soft robustness. That is, in the cases where hard robustness does not hold, let us try to choose output in the outputs in the controller which will satisfy the commitment even in those cases. That is, for those inputs which do not satisfy the relaxed assumption, you still try to meet commitment. That is, you try to maximize the frequency of occurrence of commitment for as many inputs as possible, even when the relaxed assumption does not hold. This is what I call as a soft robustness criterion. Try to maximize the relative frequency of DC holding, and we try to do this in what is called the H optimal fashion. So I don't think I'll have time to go into this theory, but basically H optimality criterion tries to maximize the frequency of occurrence of, frequency of occurrence of DC in the cases where the relaxed assumption does not hold. The way we do this is by, if you know Markov decision processes, there are these receding horizon controllers. We use a horizon value H and we try to explore, how for different inputs, which outputs we can give such that DC holds. And what we do is we try to choose those outputs which maximize the cumulative count of DC over next H moves. Now, the outputs you give will depend on what inputs you give, right? So what you do is you try to average over all possible inputs where inputs occur with certain distribution, right? So the count is averaged over all input sequences of length H. Over those inputs, you maximize chose those outputs which maximize the cumulative count of DC, and you average over different inputs. So I'm really rushing. There are lots of slides about this. You use the well-known value iteration algorithms, give utility values to outputs which, give this, and then you maximize you do some Bellman backup, which will do this. So I'm sorry, I'm really not going into this, but take it intuitively that you try to synthesize the controller which guarantees the commitment whenever relaxed assumption holds, and it tries to maximize the occurrence of the frequency of occurrence of commitment in long run on average over other inputs. Okay, this is how we will synthesize the controller. Now let's go into the logic side. How do we specify various robustness criteria and what kind of impact they have on the relative frequency of commitment holding? So robustness criterion is a formula over a single auxiliary variable called A. A is supposed to witness the actual occurrence of assumptions as given by the user. We don't know what it is. So we have this formula with this free variable A. Okay. And formula A specifies a generic method to relax the assumption. For example, the formula may be something like S count of not A is at most 3. That is, in past, the variable A becomes false at most 3. And if that is the case at any point, look at the entire past of that point. If the number of times A becomes false is at most 3, then this robustness criterion will green light, right? So it specifies that in past, assumption A fails at most 3 times. Here A is a free variable. And what we can do is we can have an assumption formula DA, and then we can compose this RB of A with DA to come up with another formula called RB of DA. It's what we call the cascade composition. Our logic has enough logical vocabulary to take such an RB of A and give you a formula which says that DA will fail at most 3 times in past, right? So given an RB of A which is independent of DA and any user given assumption DA, we are able to come up with this formula RB of DA. And I won't go into the technicalities of this, but we can construct a formula RB. By the way, in both logics, LTL and CTL, and even in PSL sugar, which is industry standard, you cannot define this RB of DA compositionally like we have done. So the logic is rather powerful. We have this temporal quantification, which allows us to do it. And then the hard robustness criterion is under this relaxedness RB of DA, DC should hold it. And whenever RB of DA is met, DC should hold, right? This should be invariantly true. Okay, so let's explore some different kinds of examples of robustness criteria. So this one formula I want to introduce, it's called suffix.
So can I ask a question?
Yes.
Yeah. So if I understand that, so here the crux is essentially the composition, but once you have the composed formula, which is this RB of DA, then the model checking will exactly work in the same way as DA is given in the input, right?
Yes. If you give directly the automaton for RB of DA,
right,
and the automaton for DC, then you can use something like Vanham Ramat to synthesize a controller which will satisfy the hard robustness. It will not optimize for soft robustness. Okay.
Yeah, thanks.
So soft robustness is something that is added on top of the hard robustness. So we have kind of a, multi-objective. The hard robustness must be met invariantly, and where the assumption, relaxed assumption fails, you should try to optimize the frequency of occurrence of commitment.
Okay.
Right?
Okay. Yeah.
So Bonham Rama did not have this soft robustness, and it did not have this relaxation of assumptions. Okay.
Yes. Yes.
Yeah. Now, how useful is this theory? How useful is it to specify robustness by logical formulae of logic QDDC? That is what I want to go into next. Okay. So, given any formula D, we can write a formula called suffix of D as given on right hand side. Don't worry what it says. It basically says that suffix of D will hold at a point I, provided all suffix intervals of the form Ji will satisfy D. That is, you take a behavior up to point I and take all suffixes of those behavior. If all of those suffixes satisfy D, then I will say that my formula suffix of D is satisfied at point I. So what I'm saying is, if I look at only the suffix part of my behavior, it should satisfy D, and for every such suffix, right? This will be useful, as you will see. Here I have a criterion called length count int with two integer parameters k and b, and it is specified as this formula given in blue and red. And what it says is all suffixes of my behavior should satisfy the formula in blue bracket. Formula in blue bracket says if my suffix spans an interval whose length is at most b cycles, then the count of violations of A is at most k. That is, if in the last b cycles, I should have at most k violations of my assumption. So it doesn't matter what happened in, beyond last b cycles. In last b cycles, I should have at most k violations. This is what this formula says. And this is the kind of reduced, this is a kind of relaxed assumption that this is a robustness criterion specifying such relaxed assumption. Now you can compose this with a user given assumption formula, and then it will say that my given assumption criterion should fail at most k times within last b cycles. This is what it says, and here is an example, but you can visualize what it says, right? This is an example. In fact, we have a kind of whole generic way of building such formulae, such relaxed assumption, such robustness criteria formulae. Maybe I don't have time to go into it, so I will skip this, but I will say that, using this kind of theory, we build a large number of, robustness criteria. And this one in green, was the one that we saw. In last B cycles, there are at most k assumption violations. Under this kind of relaxation of, assumption violation, we want to synthesize controller. And this is closely related to the K robustness criterion of Bloem and others. Here is a resilience condition, what is called the KB resilient control, robustness criterion of Heller and Topko, which says the following, you may have things going wrong, but between any two intervals where there are at most k assumption violations, there should be a period where the period of length at least b, where there are no assumption violations. These periods of length b, at least b, are called recovery periods. So all assumption violation periods where there are at most k assumption violations are followed by recovery periods of length b, where there are no assumption violations, and this too can alternate any number of times. If such things happen, you should be able to maintain the commitment forever. So this can tolerate a lot of assumption violations, but you have to give enough recovery periods. Again, you can specify this by a formula in our logic, and you can compose this with any user given this thing. So given this wide variety of assumptions, we came up with a large number of different such assumptions, some existing in literature, some new. And what you can do is you can actually order them by their logical strength. So, given two robustness criteria X and Y, you can check whether X logically implies Y, which means robustness criterion Y is weaker than robustness criterion X, which means Y will tolerate more assumption errors than X, right? And this, if X logically implies Y, we draw an arrow from X to Y. So all these criteria that we define in our logic, we order them by this logical implication, and we get a diagram like this. And the idea is that higher you go in this diagram, the more relaxed assumption you get in general for an arbitrary controller, and hence, the more robust your controller will be. So higher you go, the more robust controller you will get. Of course, which if you can relax the assumption arbitrarily, you can say that, I make no assumption, assume true. And then the controller requirement will become unrealizable. You will not be able to synthesize the controller. So the prescription is that choose the weakest or the highest such relaxation criterion which leaves your controller synthesizable, right? Now, the more relaxed the criterion you choose, you are going to get a controller which will satisfy commitments in larger number of cases. And what we did was we experimentally checked this for two problems, the bus arbiter problem and a mind pun problem. I won't do about this. Here, we are only considering the hard robustness. We are not optimizing the controller for cases where the relaxed assumption does not hold. So we are constructing what we call the maximally permissive supervisor for these problems. They have their own arbiter assumptions and arbiter commitments. Similarly, mind pump have this. And you can see that if you go back to this diagram, the highest for assume true, both these problems become unrealizable. So if you don't make any assumptions, you are not going to be able to satisfy, you are not going to be able to build the controller, right? But if you use our length burst in criteria or B currently correct criteria, B currently correct criteria says that no matter what happened in past cycles, if in the correct cycle assumption is true, then I should satisfy the commitment, So, and then there is this, race count of, which was Bloem's, or there was this rest burst in, which was that of Ehler and Topku. There are this criteria. And I have ordered this in increasing strength. And you can see that as you go to weaker and weaker, relaxations of assumptions, you are getting, what do? We synthesize the controller, and then we randomly give the inputs and measure the relative frequency of, commitment holding in long runs. So the expected value of commitment holding in long runs over randomly chosen inputs, IID inputs, right? And we count this relative frequency of commitment holding. You can see that as you relax the assumption more, the commitments hold more and more. So it is very useful to have criteria by which you can relax and the guarantee is that if the relaxed assumption holds, then the commitment will be guaranteed, right? So that is a hard guarantee. When we actually further optimize these controllers by saying even in the cases where relaxed assumptions don't hold, then also let us try to optimize the controller using all these value iteration algorithms, using receding horizon, strategies. You get a further optimized controller, and the performance of that is given in the second column. So what you find is that this optimization criterion is so powerful that all these different relaxed assumption controllers all collapse to this single controller. This optimization, soft optimization criterion subsumes all these hard optimization criteria. And you get a controller which meets the commitment in 99.8% of cases. When you use B currently correct criterion, you get another controller. They are not isomorphic, so you get different controllers. In different circumstances, they satisfy the commitment. But again, the relative frequency of commitment holding is very high. So I think I call this unreasonable effectiveness of soft optimization to meet commitment. But there are no hard, when we optimize like this, there are no hard guarantees. We don't know which are the inputs for which the commitments will hold. Whereas hard robustness will say whenever relaxed assumption is true, the commitment will hold. And what our method does it jointly optimizes the two. So you get the hard guarantee as well as you get this soft guarantee. And this is the kind of performance we get. So I think I have finished my time, and I should not go into the synthesis method. You start with this monitor automaton, and then you compute this maximally permissive supervisor, taking into account only hard guarantees, which collapses this original monitor automaton into this non-deterministic controller, which is maximally permissive. Then you optimize it using H optimality, and you get this. And all this theory I will skip. We use, as I say, an internal representation for automata as well as controllers, which is semi-symbolic, what we call semi-symbolic DFA, which originally arose in a tool called Mona. And we have developed all this, computing this maximally permissive supervisor requires computing some greatest fixed point over a set of states. Value iteration requires you to, iteratively compute, by Bellman backup the function. All this we have implemented symbolically on this symbolic automata. And the one thing I would like to say is that as a result, our synthesizer seems to be able to handle fairly large problems as compared to competition. So there is this cow competition for synthesis, and these are the winners of maybe last year. Last year's tool we have not yet compared, Acacia and Bosi, and we give the same problem instance which fit their vocabulary as well as our vocabulary, and we compare the performance of the tools in synthesizing automata. So DC Synth is our tool, and you can see that there are some problems where Acacia times out, Bosi times out on this arbiter with 6 requests and response time of 6. They are not able to handle it. There is another arbiter with a token ring built in, quite a complicated arbiter. Again, we are able to handle larger instances, and mind pump they could not handle. So it seems we, with all these optimized symbolic data structures that we use in our implementation, we are able to scale a little better, and they only handle hard, controller synthesis from B correct criterion. No relaxation, no hard robustness, nor soft robustness. So that was our tool. Amol is a first-rate implementer. We developed the theory jointly. He could implement all of this, and we built this theory. So to summarize, we developed a theory of specifying robust controllers where robustness criterion, instead of becoming a semantic criterion and having to develop separate algorithm for that, can now be written in logic. You can combine that robustness criterion with any user given assumption to get relaxed assumption, and you can synthesize uniformly using our tool and our method a controller which enforces both hard robustness as well as soft robustness. We've done a theoretical study of various robustness criteria, which are, more robust than others, and we, because we have this different robustness criteria, we can plug into the same problem. We are able to actually synthesize controllers under this different robustness criteria and to compare them for, how effectively they are meeting the commitments, the expected value of meeting commitment in long run under random inputs or under input sequences which are specified by, let us say, a finite state Markov chain, right? So we can do this kind of performance analysis, and so we are able to say, some criteria are better than that. What is the impact of soft robustness, etc. So all this was done. So that is what we have done. Now this work was presented at MemoCode conference, a joint IEEE ACM conference, where, I should give all the credit to Amol here, and he managed to get the best paper award there. So that one is for Amol. Thank you.
Thank you, Paritosh.
Little bit overshot.
No problem, Paritosh.
Yeah.
So I know there were some questions. Abhishek, do you still have that question?
Yes.
Abhishek had a question.
Abhishek?
No. Not now. Yeah.
Did you have a question, Abhishek? Abhishek, you're muted actually. I don't know. Yeah. Are there any other?
Yeah, I know. I mean, it got clarified. I mean, in the next
It got
slide.
clarified. Okay. Okay.
Yeah.
Yeah. Are there any other questions?
Can I ask?
Yeah, yeah,
one
of course.
question?
Yes.
Please,
Okay.
please, please.
Thanks. So I was just wondering about the expressiveness of QDDC. So what I understood is that possibly it's many of the properties you can write in more succinctly when compared to LTL, for example.
Yes.
But if I talk about the expressiveness, like are there properties which you can, for example, write in QDDC, but they are not expressible
So here,
in LTL?
QDDC has exactly the expressive power of regular languages.
Yeah.
Right, LTL can express omega regular languages, but you can also interpret LTL over finite words. It can only express star-free regular languages.
Yeah, but that will be like first order logic, right?
First order. So this is beyond that.
This is beyond that. So this is like you.
And in fact, I mean, that is the theoretical expressive power.
And yeah, just one. So what I was asking is that, so then it is equally expressive as MSO possibly,
It
right?
It is.
Okay.
So MSO, in fact, there is an easy translation from our logic to MSO.
I see.
Right? So you could equally use MSO. But, there is this big debate, why use temporal logics and not, classical logics like MSO, this variable. So natural, vocabularies, if you want your operators to mimic your natural language ontologies, yesterday I did this,
Mm-hmm.
Pnueli, right, in 77 argued, they were, in fact, Nissim Francis was doing his thesis under Pnueli's supervision, where he was using first order and logic to specify temporal properties. And the first paper on LTL by Pnueli deals with this issue, why temporal logic is a superior vocabulary. It's a variable-free approach to stating properties. So this is an old debate, Shibashis.
Okay.
So, for example, theoretically, MSO can do everything that we can do. You can just treat it as syntactic sugar on top of MSO.
Okay. Okay.
If you want to do that, that's fine. Yeah.
And then if I ask this question that regarding the succinctness, like is this QDDC more succinct when compared to MSO? Like
no, both have same. Okay, so the succinctness gap between QDDC and MSO, I don't know. MSO and QDDC both are Ackermann hard, so they are non-elementary,
right?
But they are harder than the Ackermann function, right?
So essentially,
I don't know whether both have the same this higher order complexity. By the way, there is a subset of QDDC, okay, called SECNL.
Okay,
which subsumes PSL sugar, right? Which has elementary complexity.
Okay.
Right? And which can naturally do, almost everything that I'm saying in practice. So, there are examples like timing diagram logics. You have timing diagram like this, and you want to describe that by logical formulae, you will be able to do it what is called compositionally and modularly in our framework. Every variable has a diagram, so you write it by one formula. First line is the diagram of, proposition A. Second line is the diagram of variable A. And every edge constraint between these diagrams, will be specified by one line. So, we'll have a formula which is linear in the size of the timing diagram. When you try to do it in LTL or even PSL, which includes regular expressions, you will lead with a formula which is of size n squared. There are other formulae where we can do it in size, to do the size linear in the size of the diagram, whereas they would have to use a formula which is exponential in size. So if you are bothered about, the size of the formula, clearly this is more succinct. But I think more important to me is this modularity. Whatever you draw, exactly that is what you write in the formula. That's just not true in case of this, PSL specification. The behavior of variable A and B and C are all getting mishmashed in the formula.
Okay.
Right? Similarly, we showed that, this composition of RBA and DA, we could define by means of a formula, right? Where was that slide? Let me. Oh dear. Okay, this one. So you give me an arbitrary robustness criterion A, like A should hold, fail at most K times in last B cycles, and you give me an arbitrary assumption formula or an assumption automaton. I can combine these two to come up with a relaxed formula corresponding to this, right? And this I can define as an operator in my logic.
Paritosh.
LTL, given an LTL formula DA and a robustness formula RB of A, possibly you will be able to guess there will exist a formula corresponding to that composition, but you will not be able to define such an operator.
Yeah, but Paritosh, I see a message on top. Maybe your computer is about to die.
Yeah. So there are two ways to resolve it. I say thank you to all of you. No, I have the power. Sorry.
No, so yeah, maybe the remaining questions. If this discussion is over, then the remaining questions, maybe we can take it in the breakout rooms that Piyush has arranged.
Yeah.
But if you have more to say for this question, please continue.
So the adequacy of logic QDDC versus LTL has been a long-standing debate, and we can talk about it a little bit offline or in breakout room.
Sure. Thanks.
So let's thank the speaker again. I mean, maybe, yeah.
Okay.
And thank you, Paritosh, very much. I mean, congratulations on the award, and also
But
it was a very comprehensive thing. Of course, I've been